All right, let's talk about the chemical properties of alkenes. They are more reactive than corresponding alkanes because they have a double bond. And that double bond can easily undergo a lot of different addition reactions. And so all of a sudden you have all sorts of reactions which can occur at that double bond. So that is a functional group. The double bond itself is a functional group capable of and possessing its own unique specific chemistry. And we can add hydrogen across it, halogens, hydrogen halides, sulfuric acid, water. Later we'll see you can form an epoxide across it. You can put like osmium tetraoxide would put two OH groups on it. There's lots of different chemical reactions we can do with that double bond. So here, this is hydrogenation. You use a catalyst with hydrogen gas and you put hydrogen across the double bond. This is exactly how margarine is made. You start with vegetable oil and you put hydrogen gas in a catalyst in your reactor and you hydrogenate a lot of the double bonds, and so your liquid olive oil now becomes a semi-solid like margarine, which is soft and spreadable on bread. And so hydrogenating vegetable oils is how we make margarine, and this is exactly how it's done. Addition reactions of halogens. And here, this is an interesting mechanism because the double bond will attack the halogen. So let's say I have bromine, but it could be chlorine or iodine, it doesn't matter which one. The double bond, these two electrons actually attack that bromine temporarily, forming partial bonds. To both carbons, and that kicks off this bromide, Br minus, which then comes around from the other direction and attacks a carbon. And so halogens are actually formed trans, so they attack from opposite sides. And both of your halogens are now attached. Addition of hydrogen halides. In this case, the double bond attacks the H, and so you grab an H, another double bond would be gone, so there's a plus on the carbon, and then the Cl minus attacks and forms a bond, and we get our product. And so that is the same mechanism for all of these. The double bond attacks the H plus, kicking off the Cl minus or the Br minus or the I minus, which then comes and attacks the positively charged carbon. Sulfuric acid is added the same way. First, the double bond attacks H. You have C plus and sulfate attacks. In general, in chemistry, when we say attacks, we mean the compound with more negative charge. Those electrons bump in, they attack the one that's more positively charged. All right, the formation of water reacts with ethene to form ethanol. Same type of reaction. It's acid catalyzed, so that our double bond will attack an H plus, and then this double bond's gone now because these electrons, these are the ones that attacked. So you have a plus here, and now water will bump into it, and then an H plus will float off to start the next reaction, and we have our product. Write the equation for the reaction of 2-methyl-1-butene with chlorine. Well, chlorine adds to the double bond, so you have a chlorine at each carbon. Addition of an unsymmetrical molecule. Two products are theoretically possible. And here we're going to use Markovnikov's rule. The hydrogen will go to the carbon that has the most hydrogens. In reality, what you're doing is favoring the more stable carbocation. And so in this case, this H will go to this carbon because it already has two H's. And so if you just remember that the hydrogen goes to the carbon that already has the most hydrogens, it'll give you the correct product. And this rule, again, is explained by the steps involved. Step 1, the double bond attacks. Those first arrows are incorrect. The arrow should always start at the electrons, and the head of the arrow should be where the electrons are attacking. So that is a bad arrow that's written in the PowerPoints. And then they grab that hydrogen, forming a carbocation. And then the chloride will then quench the carbocation. So in this case, this carbocation is more stable because it's secondary versus this one. And so that's why the positive charge forms here, because secondary carbocations are more stable than primary carbocations, and therefore the positive charge goes to the secondary carbon, which is why this is the major product. So while in theory you might have thought both would be made in equal amounts, in reality you get almost 100% of this one, and you get almost none of this one because the secondary carbocation is so much more stable. It forms so much more and so much faster that that's the reaction that occurs. So again, with carbocations, tertiary is the most stable. That is the most favored. Secondary is somewhat stable, but will form way more often than primary, which is not stable at all. And then methyl is extremely unstable. So the difference in carbocation stability is the basis for Markovnikov's rule. Predict the major products formed when 2-methyl-1-butene reacts with hydrogen. Well, we're going to hydrogenate the double bond, and we get a saturated alkane. If it reacts with hydrochloric acid, it's going to add, but due to Markovnikov's rule, this carbon would get the positive charge. This carbon would get the hydrogen. The hydrogen would go here. You'd want the positive charge here because that's tertiary. That is the most stable carbocation, which is why the chloride minus attacks there. Because that carbon is tertiary, all of your product will be this one right here. Again, in Markovnikov's rule, the hydrogen goes to the carbon with the most hydrogens to form the more stable carbocation, which then accepts the anion. And reacting with water, again, Markovnikov's rule, the carbon with the most hydrogens grabs the hydrogen, leaving a carbocation here. Water attacks there, and then an H plus splits off of that to form this compound. And when we say splits off, what I mean is there's a positive charge there, and so water attacks. So water attacks that positive charge. But what you temporarily have then is this molecule with a positive charge. And then these two electrons come back, and then this H plus floats away. And now that H plus can catalyze the next reaction. So again, it's acid catalyzed. A catalyst is never used up in a reaction. And there you go. Oxidation of double bond. Potassium permanganate is really good at this if it's a cold dilute solution, and it'll put 2 hydroxyl groups across a double bond. If it's a really harsh reaction conditions, it can actually split this in half sometimes. Alkynes. Here we have a YNE ending, so it's a triple bond, an alkyne. And again, we put the lowest number on the alkyne. The alkyne itself is a functional group. Preparation of acetylene. Here we have calcium carbide reacts with water, and you protonate it into acetylene. Reacting methane at 1500 degrees Celsius will produce acetylene. And so some very basic factories are set up just to do this because acetylene is extremely useful. Oxyacetylene torches burn at a very high temperature, and that super high temperature is extremely useful for cutting torches in welding and other fields in which they cut metal. So name the following compounds. Again, the number system comes from the triple bond. You want the triple bond on the lowest number possible. And that's why this carbon is carbon 1. And then there's a methyl group off of carbon 3. 3-methyl, 1-butyne. And -ine means a triple bond. Here, numbering from either way would put the triple bond on carbon 2, but you have a chloro, and so now the tiebreaker is which one gives that one the lowest number. If the other way would have given the triple bond a lower number, then that would take precedence. But because both directionalities, if we went this way, if we went this way, both directionalities would put the triple bond between 2 and 3. And so the tiebreaker is the next functional group coming off of it, and that would put it on 4 instead of 1. So this direction is more correct, giving you 1-chloro, 2-butyne. Properties of acetylene. It's a colorless gas at normal temperature and pressure. Very little odor when it's pure, and it's insoluble in water, and it is subject to explosive decomposition, which makes working with it kind of dangerous. Alkynes will undergo addition reactions similar to those of alkenes, but they react twice. And so when you're reacting with chlorine and bromine, they'll react twice. They'll react with the hydrohalides like hydrogen chloride and hydrogen bromide. And they react with potassium permanganate to give a positive result. Again, it's very difficult to stop it here, because in general the alkene is actually more reactive than the alkyne, and so if it reacts once, it almost always just reacts again, even faster. And again, we cover Markovnikov's rule again. This carbon got the first hydrogen because it had more hydrogens. It's forming a more stable secondary carbocation as opposed to a primary carbocation. And then the same thing happens again. And so one carbon gets both of the hydrogens, one carbon gets both of the chlorines, because it's forming the more stable secondary carbocation as opposed to a primary carbocation. So, if butane reacts with HBr, again, you want to form the carbocation here, because that's a secondary carbocation, not primary. And so this carbon gets the first hydrogen, as we see, and then it'll do that again. It'll react again, and you get another H here and another Br there. Benzene is an aromatic compound. Aromatic compounds are those that resemble benzene in structure and reactivity. And again, these are not single and double bonds. They actually all blend into each other, forming a special structure, which is why we draw it with the circle. Because it's not single and double bonds. It is a specific structural unit in which those 6 delocalized pi electrons flow throughout all of the atoms. So here we see that delocalization. So it's not single and double bonds. They're all the same bond length, and the electrons are shared equally among all 6 carbons. Substituted benzenes. The most common benzene derivatives are substituted benzenes, because it's a very common type of reaction. And so, in a monosubstituted benzene, one thing is replacing a hydrogen. Here we have nitrobenzene, ethylbenzene, chlorobenzene, bromobenzene. Methylbenzene is called toluene, and that is something you might see at Menards or Lowe's hardware stores because it's a useful solvent. You don't want to use benzene because with the way benzene oxidizes in the liver, it forms carcinogenic compounds, whereas toluene does not. So here we see toluene, methylbenzene, phenol, hydroxybenzene, styrene, vinylbenzene, benzoic acid, benzaldehyde, and aniline, which is an aminobenzene. And these names are important to know because they're used a lot in chemistry. Styrene, phenol, toluene, benzoic acid, benzaldehyde, aniline. That is how a chemist would refer to these molecules. You would never say hydroxybenzene. You'd never say vinylbenzene or methylbenzene or aminobenzene or benzene carboxaldehyde. It would be said benzaldehyde. So these special names are used, and they're commonly used by organic chemists. The word phenol represents the C6H5 group. So a phenyl group, when a benzene group is attached to something like an alkyl group, it is a phenyl group. Strangely enough, a benzyl group is a phenyl group with a methyl. And that can be kind of confusing. So to have a benzyl group, you need another carbon. And there's going to be 2 H's there. And then this can connect to something. That is a benzyl group. So a phenyl group is just this benzene ring, whereas a benzyl group is the benzene plus a methyl. And that confuses students because the naming is kind of confusing. But phenyl group is just the benzene ring attached to something. A benzyl group is a benzene plus a methyl attached to something. So here we have 3-chloro, 2-phenyl pentane. And put the lowest number on the phenyl group. Here we have diphenyl methane, 2 phenyl groups on that carbon. Disubstituted benzenes. If your first substituted product is here where G is, the second one is right next to it, that's ortho. If it's 2 away, it's meta. And if it's a 1-4 pairing, it's a para position. So that's the ortho position. So this is ortho dichlorobenzene. Here's the meta position. And here is the para position compared to that G, which is given as a reference point on the ring. The 3 isomers of dichlorobenzene have very different physical properties, different melting points, different boiling points. Here we see ortho dichlorobenzene, because they're right next to each other. Meta dichlorobenzene, because they're 1,3 to each other instead of 1,2. And para dichlorobenzene, they're 1,4. They're para to each other. And notice they all have different boiling points. They all have different melting points. They are different chemicals. When naming disubstituted benzenes, the substituents are given in alphabetical order, followed by the word benzene. So this is ortho bromochlorobenzene, because they're ortho to each other. They're right next to each other. And this is meta ethyl nitrobenzene. It's ethyl and nitro because of alphabetics. And it's meta because they're in meta position to each other. Orthoxylene, that's a dimethylbenzene, is a xylene, special name. Metaxylene and paraxylene. And so if you see xylenes at Menards or Lowe's or Home Depot, this is exactly the solvent that you're using, typically with paints or some other organic compound you're trying to dissolve or dilute. When one of the substituents corresponds to a monosubstituted benzene that has a special name, the disubstituted benzene is named as a derivative of that parent compound. So this is orthonitrophenol. You're not naming it as orthohydroxynitrobenzene. Here is para-bromoaniline. And the one that gives it the special name is the reference point. So American phenol had a special name. So this is orthonitrophenol. Aniline had a special name, so it's para-bromoaniline. Nitrotoluene, methylbenzene was toluene, so again the nitro group is meta-toluene. Naming polysubstituted benzenes. If there's more than 2 things, now we use numbers. And so you always try to get the smallest amount of numbers. Here is 2,4,6-trinitrotoluene, which is TNT, which is an explosive. Here we have 5-bromo-2-chlorophenol. Again, if there's a special named one, that is the parent compound, and the numbers are chosen to have the smallest numbers. So here we had a toluene. This should not have covered that nitro. Here we have a toluene, and the 3 nitro groups are attached to the toluene at 2, 4, and 6. Here we have a phenol, and you have a chlorine and a bromine attached. And we number it in this way because that gives us the smallest numbers. So name the following compounds. The first one, we have 1-ethyl 2-fluorobenzene, or we could name that ortho ethylfluorobenzene. They'd both be correct. 3-nitrotoluene, or we could say meta-nitrotoluene. And here we have 2-bromo, 1-chloro, 4-nitrobenzene. And now there's 3 substituents, so there is no, you're not going to use ortho or meta or pair there. That works best when there's only 2 substituents. When there's 3 substituents, we use the numbers and you number it to get the lowest possible number set. And this is 1, 2, and 4. Going the other way would be 1, 2, 3, 4, 5, 6. It would be 1, 4, and 6, which is not as low as 1, 2, and 4. And that's why the numbers go that way, to get the lowest numbers possible, because that makes it more correct.